Good day, I'm Dr. T and welcome to my office. So today I'd like to talk about describing imperfection in measurements. As humans, we're not perfect, and nothing that we do will ever be perfect, but we can put more effort into things and get higher quality results, or we can take a few shortcuts and not get the quality we wanted, but not put nearly as much effort in there. Good day, I'm Dr. T and welcome to my office. Good day, I'm Dr. T and welcome to my dining room table. So today I would like to discuss the imperfections in measurements and the way that we communicate them. We're mortal. Nothing that we do will ever be perfect. But when we do things, if we put a lot of effort in, we can get a high quality, tons of accuracy and precision, or we can sacrifice some of that accuracy and precision to make our task much easier. Now, of course, depends on what we're doing, depends on which way we want to go. It gets a bad rap going for quick and dirty, but sometimes if it's good enough, then it's good enough. Other times, if it's not good enough, then, well, you got to put in the hard work. But more importantly, you actually need to communicate how good this actually is. Because if I think the number is of high quality and I use it, but it's actually a low quality number, well, then that's going to be a problem. But if I know that the number is not of particularly high quality and I'm going to need the high quality number, I know I have to measure. If I don't need a high quality number, then hey, it's good enough. So how do we do this whole communicating thing? As chemists, one of the approaches that we like to use is known as significant figures, or SigFigs. And let me give you a few examples of this. So let's start out and let's say I have a number 123 meters. Okay, so in this case, I have a number, it says 123 meters. The way I've written it implies, due to significant figures, that the true value, whatever the length of this thing is going to round to 123 meters. Meaning that my true value is going to be somewhere between 122.5 meters and 123.49 repeating meters. This way I am saying, hey, this is what I know my true value to be. It's in this range. Now, if that's good enough for your functions, whatever you're doing with this 123 meters, great. If that range is too large, well, you'll have to remeasure because I don't have the accuracy or the precision for you if that is what you need. Now, this is fairly straightforward. Let's actually look at a couple other examples of the way we might look at this. Okay, so let's make things a little bit interesting. Okay, I have 0.123. Okay, it's going to be 0.122 because I miswrote that. You'll notice I started the number off with a 0. This is what I call a safety 0, and this is to make sure it doesn't accidentally look like 122. It looks like 0.122 in case I were to have drawn the decimal point in such a way that you might have missed it. Of course, I need a unit on this. Okay, this is the same as the last one. This is going to be fairly straightforward. This is going to be 0.1225, that's a 5, meters to 0.12249 repeating meters. Okay, same scenario as last time. But let's do some other interesting things with this. Let's say I have 12.0 meters. Now, in this case, this 0 is actually doing double duty. Well, I shouldn't say double duty, it's kind of doing single duty. It's indicating that I do actually know what that back number is. So I know that this guy is somewhere between 11.95 meters to 12.049 repeating meters. So this is narrowing my range. That 0 is telling me that, hey, I've actually measured this and I've narrowed it down. However, if that 0 was on the other side of the decimal point, things could be a little bit more confusing. So I could have 120 meters. Now, at this point, there's a bit of a debate. The way I have it written here is pretty much agreed that this is saying that it is between 115 meters and 124.9 repeating meters. That 0 is a placeholder. It's not indicating that that is particularly measured. That is part of the rounding. And yeah, now what if I want to indicate that no, that is actually part of the number I've measured. That 0 is significant. There's two schools of thought to say. One is I could rewrite this. And in one school of thought says that I could simply rewrite it as this. I put the decimal point in. In that case, this would definitely be 119.5 meters to 120.49 meters. That decimal point then makes the trailing 0 significant. Alternatively, though, there is a second school of thought that says, you know what, that's kind of vague, and that if I want to write this, I really should write this as 1.20 times 10 to the second, and simply put that into scientific notation. Well, yeah, we've got some written numbers. Let's actually use this in some math, because this is actually going to make life a little bit more interesting once I switch this over to math. So the dominant mathematic operation that as chemists we're going to do is multiplication and division. They're going to behave very similar because they're essentially just inverses of each other. So let's do some math. Let's say I have 1.23 meters times 2.6 meters. So apparently I'm doing area. Okay, so I'm going to multiply those, and I'm going to go ahead and type that in my calculator. And that gives me 3.198 meters squared. The units are treated very much like variables would, even though they are definitely not variables. So meters times meters is meters squared. Now, how do I figure out where I need to round my number? And the point out actually I should make is that I do need to round this number because I want to make sure I indicate that this number is to what the true number would round it to. And so, well, how do I know that? For multiplication or division, so this could be a divide by here, what I want to do is first look at each of my numbers. The answer is only going to be as good as the parts that you put into it. So, if I look at this number, I see 3 digits here that are all good. So presumably, my answer will, or this value would round to this number. Otherwise, there's a problem. So this has 3 digits that are of high quality, or what I would call significant figures, or SigFigs. The second number only has 2 digits. They are once again presumed to be of high quality and are significant. Therefore, I would say this has 2 significant figures. Now, for multiplication and division, the rule is that the answer can have no more significant figures than any of its constituent parts. Therefore, since this has 2 significant figures and this has 3 significant figures, it cannot have any more than 2 significant figures. This is the weakest link. Therefore, I need to round mine to 2 significant figures, and you start from the left going over. Therefore, this would be 3.2 meters squared. And you're thinking, but wait, you just threw away all those wonderful numbers. Well, I threw away numbers, but they didn't have meaning. I couldn't trust them. They're not of high quality. Now, when doing this, it gets into a couple of interesting questions that lead kind of into what I was going to begin with. So let's do another mathematical operation. And I will stick with my classic 1.23, but in this case, I'm going to have 2.60 meters. Let's make my dot nice and big. Well, in that case, I'm still going to get 3.198 meters squared, but I'm still going to have to round. However, in this case, something is slightly changed. This is still 3 significant figures. It's the same number. This, however, notice how I now have the 0. Remember when I talked about earlier how that 0 kicked back my range? Well, it does the same. So this is going to have 3 high-quality numbers, 3 significant figures. Therefore, the least number of significant figures is 3. This is 3 significant figures. Therefore, my final answer would be 3.20 meters squared, because I'm rounding to here. The 8 rounds the 9 up, and of course that turns it into a 0, with the next number going up by 1. Okay, this is going pretty good. Now, when mentioning this with the least number of significant figures, I do need to point out something real quick. Depending on the nature of these units, things can change. Meters are units that would have been measured, so everything I've said so far holds true. If, however, the unit I have is some form of definition, so let's say I was to do an equation such as 1.23 meters times 100 centimeters per meter, my meters would cancel, and I would be left with 123 centimeters. Now, when it comes to significant figures, this guy still has 3 significant figures, but this number is exact. This is part of a definition. 100 centimeters equals a meter. It's not a fraction, and there's no other variation. If it doesn't equal, it's not a meter. Therefore, we don't worry about significant figures here. It's as if there is an infinite number of significant figures. Although usually we just say it is exact. Now, definitions are one source of exact numbers. An alternative source would be a count. In that case, the way you measured something by literally counting 1, 2, 3, 4 is such that there could be no imperfection in that particular measurement. There could be mismeasurement. You could miscount. But it's not like you could have, say, a fraction of an individual. If you walk into a classroom, you would have, say, 24 students. You are not going to have 24 and a half students, because there's no such thing as a half student, or if you had half a student, you'd be calling the police. So for exact numbers, definitions and counts, we just simply ignore them. Treat them as if they're an infinite number of significant figures and look at the other digits. Now, what gets slightly interesting is cases like up here, where we have to count a little bit more interestingly. So let's say I take 1.023 times 120, and we're going to keep these as meters. And what will this equal? So I grab my calculator. I make sure my paper is still aligned. Grab my calculator, 1.023 times 120, and I get 122.76 meters squared. Okay, so in this case, when counting significant figures, in this case, I have 4 numbers. Sometimes you'll hear this referred to as a sandwich 0. It's just a normal number. You don't have to worry about it. So this is 4 significant figures. In this case, I have 2 non-zero numbers, and I have a 0. This is just like this particular case, because there is no decimal point. I know that that 0 is not significant. It has been rounded away, presumably. So this is 2 significant figures. 2 is less than 4, so we're going to run with 2. This will be 2 significant figures. Therefore, that is where we round, and this will turn into 120 meters squared. Okay. Fairly straightforward. If you're looking at certain sources, you will see numbers listed in a couple of different ways. You will see the safety 0, or alternatively, any zeros to the left of the number. This might be referred to as a preceding 0, and those would never be considered significant. So if I was to have a number, say 0.00123 meters, that would still be 3 SigFigs. Let's see if I can actually get that on my paper. I think you can there. That's a little easier to see. Okay. So anything before the number would not count. Anything after the number, if there's a decimal point, those usually do count. If there's not a decimal point, then those usually do not count. Now, there is one more type of mathematical operation that we typically use, and that, of course, is addition and subtraction. So let's look at those. So in this case, I'm going to have two sets of numbers, and I'm actually going to move my paper so it's a little bit more in the center. So let's say I have my 123 meters and I subtract off, say, 32 meters. Okay, 2 points to take place. First, if I'm doing addition and subtraction, my units must match. In multiplication and division, my units don't have to match, and they will simply multiply and divide themselves. Now, I've got this guy. I can grab my calculator. 123 minus 32 is 91. But the question, where do I round to? Well, I don't actually count significant figures in this case, because that's not what's governing the error in my particular measurement. In multiplication and division, the error was equally influenced on each one. However, in this case, it's actually where they fall past the decimal point. So in this case, I have 1, 2, 3, point, I don't know. I don't know any numbers after the decimal point. I also have 32 point, I don't know what. So now, I don't know what minus I don't know what is I don't know. And then the rest of the math runs like normal. Okay, that's the exact same answer. What do you get net? Well, let's try this again with some slightly different numbers. Let's say I take my 1, 2, 3, and I subtract off not 32, but 3.2. I grab my calculator, I run this again, and I get 119.8. And these are all still meters. Okay, so I'm going to line these up again. See if I can write the number 2. Okay, question mark minus 2. I don't know. I don't know what that number is up there because that's part of it that's been rounded away. Now, 3 minus 3 is 0, 2, 1. Yeah, I only get 3 significant figures on this one. I have to stop at the ones place because the 1, 2, 3 stopped at the ones place. So thus, I have to round here. And in this case, it just does happen to line up in this case so that this would equal 120. That's kind of a dumb luck in this case. Okay, so with addition and subtraction, what I want to do is look for the number that goes the least past the decimal point, or its last number that's significant is in the largest place. And that's going to dictate where I have to round to. This was in the ones, that was in the tenths. I had to round to the ones place. The only other caveat I should bring up is that occasionally, most so when you're doing multiplication division, you could actually happen to get a number that has less significant figures on your calculator than what you need. And in that case, you simply just add zeros at the end. So I could imagine taking 9.0, dividing that by 3.0, and my calculator would give me 3. Now, of course, I would need 3.0 because those two numbers have 2 SigFigs, while my calculator only gave me 1 SigFig. And we could say something like meters squared, meters, meters, meters. Okay. So I hope that's a brief introduction to significant figures. They're a little bit weird to start with and take a bit of practice, but once you get used to them, you're usually not too bad. As chemists, we like using these because once you're used to them, they're actually very easy to use. There are other ways of describing the uncertainty within your numbers, and those other ways are actually, in many respects, better and more powerful, but they tend to be a bit more work. So significant figures are a nice balance between describing the amount of imperfection in your number and the amount of work you actually have to do. Of course, everything takes practice, and I do realize that this is something that most people haven't run into too much before now. So with that said, have a wonderful day.